Hello everyone, welcome back to This Is Not a Science channel, and today we'll talk about the periodic table. And this is actually a continuation video from the previous chemistry video, so make sure you check out that one before you watch this one. I'll put the link in the description. A lot of things that we talk in this video will be based on knowledge that I taught you guys from in the previous video. So make sure you check that out first, and you can come back to this one where we will look into detail of periodic table and how do we actually understand it and how do we use it. Well, the previous video we ended up around here where I showed you guys the full periodic table, and I slightly introduced the concepts of groups and periods and how it actually sorts out the periodic table. Well, now we're going to actually look deep into it. So if you remember from the previous video that we have such thing as, here we got the metals, and we got the non-metals, and we have around here which is the transition metals. So these guys are the main components that we will look into while we're looking at the periodic table, because these are the most important ones. The ones below there for a higher level of studying. So if you're interested in chemistry, I will make more videos about the ones below. They are the actinoids and lanthanoids, but then we'll talk about that later. So let's just look into the periodic table and the concept of groups and periods. So when we look into it, there are some names that we must remember regarding the periodic table. So you should be confident that everything on the left-hand side of the periodic table, including the transition metals, those are the metals. And everything on the right-hand side should be the non-metals. And here are some names that you need to remember. So if you remember when we talk about groups, group 1 right here, so this vertical column right here, these are what we call the alkali metals. So that's the name for group 1. And if we look here, halogens, group 7, which is around here, these are the halogens. So we have the alkali metals and we got the halogens. And then I have to introduce something called the staircase. And the reason why we have this is because this is a clear line to separate between metals and non-metals. And the staircase I refer to is around here. If you look below boron, we got aluminium right here. So this is this kind of zigzag staircase pattern right here, and this separates the metals and the non-metals. So you can see my circle actually circling the whole area here, but then the actual non-metals actually starts here, so beyond this staircase where we have silicon. And so basically everything beyond this side of the staircase will be metals. Everything on the right hand side of the staircase will be non-metals. And we refer to these ones as metalloids. Okay, because they're not really metals, but then they're not non-metals. They're just in between, so we call them metalloids. And at last we have group 8, and they are the noble gases. Group 8 is around here. This entire column, we call them the noble gases. It's because they are really unreactive. So we'll talk about them, but not much, because they don't react much with other elements. And the reason behind this is because they have a full outer shell. And I'll explain that later, why noble gases do not usually react. Let's get into the concept of learning how to group elements. So the numbers here on the top, these represents the group, which is the vertical columns down. So we got group 1, group 2, group 3, group 4, group 5, group 6, etc. But why are they grouped like this? Why do we have numbers like this? Well, we're going to explain why later. So here's a small task that I would want you guys to try. So I got lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And I want you guys to try to draw the atomic structure of these. So remember from the previous video, we have the we have the cross diagram of these elements, and try to draw these elements out. And I recommend you, while watching this video, you have a periodic table right next to you so you can know where these elements are. But actually I already told you guys the electron numbers here, so just try, give it a go, draw these atoms out. I hope you guys try to draw the atoms. Now I'm going to review how they actually look like. So we got lithium. So we got 3 electrons. If you remember from the previous video, we are only allowed to have 2 electrons in the first shell. So we got 2 electrons here. And 1 additional electrons in the outer shell because it has 3 electrons. Well, beryllium, we have 4 electrons. So we got 2 in the outer shell. And boron, we have 5. So we have 3 in the outer shell. Carbon, we have 6. So we have 4 in the outer shell. Nitrogen, we have 5 outer shell because it has 7 electrons in total. And oxygen, we have 8 electrons, which means 6 electrons in the outer shell. And fluorine, we have 9, so it's 7 electrons in the outer shell. And neon, we have a full outer shell of 8. Because remember, neon is a noble gas. So noble gas always have full electron configuration, which means the outer shell is always filled. So once we looked at this, can you see a pattern now? Electrons tend to increase across the period. So if we take a look at the previous slide, we have group 1, group 2, group 3, group 4, group 5, group 6, group 7, and group 8. Can you notice one thing? Once we go across, our electron number actually increases. So if you look at lithium, we have 1 electron on the outer shell. Beryllium, we have 2 electrons on the outer shell. Boron, we have 3. Carbon, we have 4. Nitrogen, we have 5. Oxygen, we have 6. So these group numbers actually represents the number of electrons on the outer shell. So in the future, when someone asks you, for example, how many if someone asks you how many electrons are there in the outer shell of iodine, well, you don't have to count. You can straight away tell me it's 7 because it's in group 7. So now you can understand that the group number actually stands for the number of electrons in the outer shell. So for instance, if someone asks you what's the outer shell electron of sulfur, for example, you know it's 6 because it's in group 6. And if someone asks you about calcium, you know it's 2 because it's in group 2. So this is why we group it like this, according to the number of electrons in the outer shell. So next up we have the periods. And the periods are actually related to the groups, except they're just horizontal. So these numbers here represents the horizontal rows in the periodic table. So you can see period 1, 2, 3, 4, 5, and 6. So another task that I want you guys to try is to sketch also the previous atom diagram for these ones. So we got hydrogen, lithium, sodium, and potassium. And in this case, I also told you about shells. So the number of shells that they have. So we see hydrogen, we have 1 shell, lithium 2 shells, sodium 3 shells, and potassium 4 shells. And just try to arrange these electrons inside the shells and hope you can spot a pattern right here. Okay, I hope you guys have your diagrams drawn. So we got hydrogen where we have 1 shell and 1 electron, so that's simple. So it's only 1 electron in the outer shell. Well, lithium, we have 3 electrons, but we need 2 shells because we know the first electron can only contain 2 electrons. So the third electron must be in a new shell. While sodium, we got 2 electrons in the most inner shell, 8 electrons in the second shell, 1 electron in the outer shell. So we realize that we got the second shell, which is 8 electrons, because other shells, most except for the inner shell, the other shells can only fit 8 electrons maximum. And we got potassium right here. Potassium, we have even more shells. We have 4 shells because we have to contain 19 electrons. So with 2 electrons in the first shell, and the other 2 shells all have 8 electrons. So have you spot a pattern right here? We have the same number of valence electrons. We have the same number of outer shell electrons. And this is true because if we remember from the previous description of groups, these elements, they are all in group 1. So logically follows that every elements in group 1 should have 1 electrons in their outer shell. So we know that everything group 1 has 1 electrons in the outer shell. And how does the period work then? if you take a look at this 1, 2, 3, and 4, and if we take a look back at our periodic table, hydrogen is in period 1, lithium is in period 2, sodium is in period 3, potassium is in period 4. So these periods suggest the number of shells that the elements have. So if you're in period 1, you have 1 shell. Period 2, you have 2 shells. Period 3, you have 3 shells. Period 4, you have 4 shells, and so on. So it's actually really easy now. If someone asks you, for example, how many shells does, for example, xenon have? Well, you can immediately tell them that xenon has 5 shells because it's in period 5. So it's actually very simple how you use periods and groups together to determine the number of shells and the number of outer shell electrons. So for example, again, someone asks you, how many shells does iodine have? Well, you know it's 5 because it's in period 5. And how many outer electrons? You know it's 7 because it's in period, it's in group 7. So in this case, you can work out the information of an atom really easily. Now let's slightly talk about bonding. Once we've actually understand how the periodic table works, we'll take a look at how stuffs react with each other, because chemistry is really interesting. There's all sorts of reaction going on, and they're so different, and we must learn every single one of them because they are all important in our lives. So when it comes to bonding, it basically means a reaction. Whenever something bonds together, there is always a reaction. And we're going to briefly introduce different types of bonding, while in our next video we will continue to detailedly describe how every single one of these bonding works. So first of all, we have ionic bonding. And ionic bonding basically means, if you take a look at our periodic table, it's 4 metals. So metals, these ones, transition metals, or the metals on the left hand side, metals reacting with non-metals. So here are the rules. It's always a metal with a non-metal. It has to be. That's the rule. So every time when you try to identify if something is ionic or not, take a look at the composition. If it's a reaction between a metal and a non-metal, then it's definitely ionic. And there is always a transfer of electrons. So what does that mean? We'll explain that in the next video, what transfer of electron actually means. And the other property that you need to know is ionic bondings are really strong. They're really hard to break. So example, sodium chloride, NaCl, which is some common table salt, the salt that we add in cooking. And we have Ki, potassium iodide. We have MgO, magnesium oxide. And we have CaBr, calcium bromide. And if you take a look at them, they all have one thing in common. It's always a metal with a non-metal. So if you take a look at that, sodium, it's around here, sodium with chlorine, which is a non-metal, so that works. Or potassium iodide, so we have potassium right here, and iodine right here. Or magnesium oxide, we have magnesium right here, and oxygen right here. Same thing with calcium bromide, we have calcium right here and a bromine here, so it works. Next up we have covalent bonding, and covalent bonding is different. Covalent bonding, we are only limited to non-metals, so it's only suitable for non-metals. So here are the rules. They're only for non-metals, and they share pair electrons. So in this case, they share electrons instead of transfer, which is different from ionic. And covalent bonding, they're really weak. So the forces between the molecules are really weak, not like ionic bonding where the force is really strong. So covalent bonding, whenever you're trying to identify if something is covalently bonded, you have to take a look at their composition. If they are all non-metals, then it works. And remember, non-metal is the ones behind this staircase right here. So these are the non-metals. So examples, carbon dioxide, which I bet everyone knows that carbon dioxide is one of the most serious greenhouse gases. And we have nitrogen trioxide, and we have chlorine. So if you take a look, CO2, C, carbon, it's a non-metal, and oxygen is a non-metal, so it works. And we have NO3, nitrogen is a non-metal, oxygen is a non-metal, so it works. And Cl is just Cl bonded with itself, so we have two chlorines and they're both non-metals, so it works. The final one, we have metallic bonding, and this one is the exact opposite to covalent bonding, because from the name I guess you can tell metallic bondings are only limited to metals. So it's rarely when we use the metals on the left, which are the alkali metals, but metallic bonding happens really often between the transition metals. So here are the rules. They're only for metals, and another important feature is that they conduct electricity. So what does that mean? It means it's really it's very linked to industrial processes, where examples are alloys. So these alloys, they are actually a mixture of different metals in order to achieve different properties, because next episode when we take a look at transition metals, their properties are actually very special, and you can mix them together to achieve different materials for industrial uses. So this is the last type of bonding that you need to know. I guess this is it for this episode, and make sure you like the video and you subscribe to my channel. It took me quite a while to make these videos, and share it to all your friends who hate science. In the next episode, we'll talk about how these bonding actually works, and they're really interesting because you can see the chemistry inside the atoms and how they actually interact with each other. So make sure you subscribe and you stay tuned to the next video. Thank you, and see you next time.